Hi, my name is Kwangbin Bae. In this video, I will present the work IronDepth, Iterative Refinement of Single-View Depths using Surface Normal and its Uncertainty, which was done jointly with Ignaz Budvytis and Roberto Cipolla. Let's talk about monocular depth estimation. Given a 2D image as an input, our goal is to estimate the metric depths of each pixel. Following the success of deep learning, the accuracy of learning-based depth estimation methods has improved significantly. The RMSE is only about 30 centimeters for indoor scenes and about 2 meters for driving scenes. Despite the high accuracy, the existing depth estimation methods have limitations. Firstly, they are poor at generalization. Inferring the physical distance to an object is a difficult task, and the network should rely on high-level cues. For example, in order to estimate the distance to a car, the network should first learn how to recognize a car and learn the relationship between its apparent size in the image and its distance from the camera. When presented with an object that was not included in the training set, the network can fail to predict the right geometry. The prediction is also biased to the physical scale of the training scenes. So if the network is trained on small rooms, like the ones in NYUV2, the accuracy is likely to be lower for large rooms in IBEAMS 1. Secondly, the existing depth estimation methods have poor surface normal accuracy. Here are some of the predictions made by a state-of-the-art method. While the predicted depth maps look convincing, when you visualize them into point clouds, you can see that the walls are not flat and they are not perpendicular around the corners. We believe that this is because we are using CNNs to directly regress the depth map. Suppose that there is a flat surface and an image plane. If we use orthographic projection, the gradient of the depth map will be constant within the surface. However, we are more interested in perspective camera, and for perspective projection, the depth gradient is dependent on the viewing direction. This makes the problem particularly difficult for CNNs, which are inherently designed to be translation equivariant. Our idea is to use surface normal, which is constant within a flat surface and is thus easier to estimate using CNNs. In our previous work, we estimated the aleatoric uncertainty in surface normal estimation by predicting the surface normal probability distribution and minimizing the negative log likelihood of the ground truth. We introduced a new parameterization for the distribution to make the training more robust against noisy ground truth. We then used the estimated uncertainty to improve the performance on small structures and near object boundaries. We achieved this by training pixel-wise refinement MLPs on a subset of pixels selected based on the uncertainty. As a result, we were able to estimate the shape of small, thin structures with complex geometry. Since the surface normal can be estimated from local, low-level cues like shading, the network can generalize well to unseen objects such as humans, animals, and cars. We could also see that the estimated uncertainty correlates well with the prediction error. So, by removing the pixels with high uncertainty, we could identify the pixels for which the predicted surface normal can be trusted. While surface normal cannot give us the metric depths, it tells us how the depths should change around each pixel. The goal of this paper was to exploit such geometric constraint and improve the quality of monocular depth estimation. Our idea was to use surface normal to propagate depths between pixels. Suppose we have some initial depth prediction. For each pixel, we can define a local neighborhood. Let's call this pixel I and call this pixel J. For pixel J, if we have some initial estimate on its depths and normal, we can propagate that information towards pixel I. The value of the propagated depths can be calculated using camera intrinsics, and this can be done for every pixel in the neighborhood. We can then treat the propagated depths as candidates for the refined depth map. The weighted sum of these candidates will give us the refined depth map, and the process can be repeated multiple times. In other words, we can formulate depth refinement as classification of choosing the neighboring pixel to propagate from. For neighborhood size, we chose 5 times 5, which gave a good balance between accuracy and computational efficiency. The normal guided depth refinement is performed in a coarse resolution. This allows the network to handle long-range dependencies with relatively fewer number of iterations. After the refinement, the resulting depth map should be upsampled to match the input resolution. However, if we use bilinear upsampling, it will not preserve the surface normal. Our idea is to use the normal guided depth propagation, which was used for coarse resolution depth refinement. The only difference is that now we are propagating to subpixel points. For each pixel in the high resolution depth map, we propagate from its 3x3 coarse resolution neighbors. Here is the IronDepth pipeline. Given an input image, we first use a pre-trained network to estimate the per pixel surface normal and its associated uncertainty. We then use another network to regress the initial depth map and produce some context feature. Given the coarse resolution depths and normal, we can propagate the depths between the pixels to get the per pixel depth candidate. Then the context feature and the surface normal uncertainty are fed to a recurrent network to estimate the weight for the propagated depth candidate. The weighted sum will give us the refined depth map, and this process can be repeated multiple times. Lastly, the refined depth map is upsampled by the proposed normal guided depth upsampling. The number of iterations is set to 3 during training and 20 at test time. The training loss is the weighted sum of the L1 losses, where gamma is set to a positive value less than 1 to put a bigger emphasis on the final output. Here we demonstrate how the proposed framework refines the predicted depth map. Here is an input image, the predicted surface normal, and the associated uncertainty. Here is the initial depth map visualized into a point cloud. In this example, there is a bed, which should have a rectangular shape and should be parallel to the wall. While neither of these characteristics is captured in the initial depth map, IronDepth can recover the right geometry using the predicted surface normal. IronDepth is not only useful for large planar surfaces. It can recover the shape of small objects and curved surfaces. In this example, the distance to the door is adjusted by flattening the floor. Here is a qualitative comparison against Adabin's. While the depth maps look similar, the point cloud comparison shows that our method is better at capturing the orientation of the surfaces. Quantitatively, we achieve state-of-the-art performance on NYUV2. While the differences in depth metrics are small, the surface normals computed from our depth maps are significantly more accurate than those obtained by the other methods. Here, the methods are trained on NYUV2 and tested on IBeams 1 without fine-tuning. Similar to the results on NYUV2, we achieve a small improvement in depth accuracy, but a large improvement in surface normal accuracy. For IBeams 1, there are additional metrics which quantify the planarity of the pixels belonging to walls, tabletops, and floors. In both metrics, we significantly outperform the other methods. Here we demonstrate the generalization ability of our method. Despite being trained only on NYUV2, the network can generalize well to ScanNet, Middlebury, and Kitty. Besides the state-of-the-art performance, the proposed normal guided depth refinement has two additional benefits. Firstly, the initial depth map can be replaced with the predictions made by the existing depth estimation methods to improve their accuracy. Secondly, the proposed framework, which was trained only for depth estimation, can seamlessly be applied to depth completion, where sparse depth measurements are available. Given the measurements, we can simply fix the depths for the pixels with measurement and apply the normal guided depth propagation so that the information can be propagated to the other pixels. Alternatively, we can adjust the scale of the prediction based on the measurement before fixing the depth. For both scenarios, we could observe meaningful improvement in the accuracy, showing that IronDepth can also be used to tackle depth completion. To summarize, we proposed the normal guided depth propagation for depth refinement and upsampling. We achieved state-of-the-art performance on NYUV2 and IBeams 1. Lastly, we explored the benefits of using surface normal to propagate depths between pixels. The proposed framework can be used to improve the accuracy of the existing depth estimation methods, or to solve depth completion, where sparse depth measurements are available. Thank you very much for listening.